In this video, we're going to summarize what we've seen so far in chapter 29 of the OpenStax textbook, if you're in my course, and talk about a few practical things that you might see sometimes. And so, first of all, I've given you two values of Planck's constant. First is what we've seen before in a video, 6.626 times 10 to the negative 34th joules seconds. But remember, when we're dealing with the small amounts of energies that we typically deal with when we deal with atomic and electron systems, we usually substitute for a joule an EV, which is a much, much smaller unit of energy. If you remember the conversion, 1 electron volt, or 1 EV, is 1.602 times 10 to the negative 19th joules. And so instead of writing all this, instead of writing the long form of a joule, we typically just make it a lot smaller by converting it to EV. It's easier to write, it's easier to keep track of, and we can always convert later. So I've given you that value. I've also given you the value for Planck's constant in electron volts seconds, or EV seconds. Which one of these you pick out depends on your application. If you're dealing with something in which you need joules, you will probably use this one. And recall what that means. If you're doing something where you need something like a speed of something in meters per second, you're going to need to use joules for that, because inside a joule is a kilogram meter per second squared, which is a Newton, times a meter gets you a joule. And so something like that, you will need joules. If you're just dealing completely with energy, probably you're going to use this value, the electron volt second value. But it just depends on your application, and you sort of have to play that by ear and see what happens. One thing that you will see if you look in other textbooks, our textbook doesn't really deal with this, but a very common thing to do to Planck's constant is to divide it by 2 pi. The symbol for that is h bar, is what we call it. It's just an h with a slash through it, slash through the stem there. It's another constant. It's Planck's constant divided by 2 pi, which is yet another constant. There are lots of applications where this turns out to be useful. Again, it's just convenience to keep us from having to write all this over 2 pi all the time, which pops up in some systems. So you might see this written at some point. Another really practical thing we can do is, remember when we looked in the last video about the energy of a photon, we found that the energy of a photon was equal to Planck's constant times the frequency of that photon. It might seem strange to talk about a particle of light having a frequency, but quantum mechanics is strange. What are you going to do? So one of the things we like to do to, again, make it easier on ourselves is to remember that F for something involving electromagnetic radiation is characterized as c over lambda. This comes right out of the wave speed equation. Remember, c is equal to f lambda. If I just solve this for the frequency, I get c over lambda. And that turns out to be useful because very often we characterize electromagnetic radiation in terms of its wavelength. That's usually in nanometers, because visible light has a wavelength range between about 400 to 700 nanometers, somewhere around there. So it turns out that it's really handy to characterize light in terms of its wavelength. So I can also write this energy, of course, as hc over lambda. There's nothing different about these equations except for how they're expressed, right? The relationship between frequency and lambda through the speed of light is well defined, and so I'm not creating anything new. I'm just writing something in a little bit more useful form. And this turns out to be even more useful if you notice that Planck's constant and the speed of light in vacuum are both constants themselves. So if I run this calculation, if I take Planck's constant in electron volt seconds form and the speed of light in meters per second, although I'm going to need to transfer to a different length unit like nanometers, if I run this, what I get in the numerator is about 1240 electron volt nanometers. And you can just sort of hang on to this. Now, do you need to know this number? Do you need to memorize it? Absolutely not. You can always run, if you need to perform this calculation, you can always plug them in and run through that. But if you know that HC, I should do this, if you know that HC is equal to 1240 electron volt nanometers, it's just a time saver. You can just sort of plug that into your calculator, divide by the wavelength. Please notice, though, that you will need the wavelength expressed in nanometers for these units to cancel. If it's not expressed in nanometers, you need to convert to nanometers. And then that will leave you with energy with units of electron volts. If you need it in joules, you will have to convert again using the EV to joules conversion, which is again something easy to look up. But this is just a little time saver. It's not required to be able to know that, like I said, but there are many, many times where that just sort of saves you a lots of time. Okay, all right. Another thing to talk about, we've talked about the energy of a photon. Well, you know, quantum mechanics is not content with being that strange. It gets even stranger. We can talk about the momentum of a photon. We're actually going to define this as h over lambda, where lambda is the wavelength of the photon, just like it is here, and h is Planck's constant. Notice this differs from the energy by a factor of c. But if you really think about it, if you think about what we used to know momentum as, mv, okay, well, fair enough, but if you realize or remember that a photon has no mass, in some sense, the idea of what is meant by the momentum of a photon is a little bit silly, honestly. The first time you see it, you go, well, what does that even mean? Because it has no mass, and mass is crucial to the idea of momentum for matter. But it turns out that photons also have momentum. One of the reasons this might be surprising is because you never really observe it, because Planck's constant, no matter which form you use, is a tiny, tiny number. And this is going to, the numerator here is most likely going to dominate this ratio. And so the momentum of a photon is really, really, really tiny. So think about it. If you have a mirror and you bounce a photon off a mirror, what does the mirror do? Absolutely nothing, right? If this were some sort of like a baseball or something and you bounce it off something that was standing up, whatever it is that you bounce it off would probably fall over because there would be some sort of recoil, right? The ball exerts a force on this thing, which then usually topples over or at least wiggles around a little bit. But the momentum of a photon is so tiny that we don't see it occurring here on the Earth, right? The friction between this mirror and the surface it's resting on is far, 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 far greater than any sort of force imparted to this mirror by the photon. However, if you are somehow able to remove things like friction or air resistance, you actually would see a reaction. So if you've ever heard of something called a solar sail, this is an idea that actually has been utilized somewhat to basically attach a large sheet of reflective material to a spacecraft and use the actual photon momentum from the sun bouncing off that solar sail to propel a spacecraft. Now, at the beginning, there's not a whole lot of momentum, and so this thing doesn't go very fast, but as collisions keep occurring, the momentum is transferred and it builds and it builds and it builds, and sooner or later you can achieve some pretty reasonably high velocities with this idea. This is based upon an idea called radiation pressure, which is really nothing more than a transfer of momentum from collisions with photons. So do we see it here on the Earth? Not usually, or at least not macroscopically. We see it microscopically, of course, but macroscopically we don't ever see this because this momentum is so small. But if you are able to remove any mitigating factors like friction or air resistance, you actually do begin to see the effects of this photon momentum and any sort of transfer momentum that might take place. Really, really very interesting applications of this and very interesting problems that you can work with that. All right. To sum up what we have seen so far about light, we have seen light, that is to say electromagnetic radiation. Because when I say light, we typically think of visible light, but really X-rays, gamma rays, infrared waves, all of them are the same thing that we're talking about, electromagnetic radiation. Can exist as a wave and a particle. We conclusively showed that it was a wave when we saw the Young's double slit experiment, and we saw an interference pattern appear after you pass light through a barrier with small openings in it. Small enough so that the light diffracts, and as it passes through, forms waves on the other side. It forms a different shape of wave on the other side. Remember what that looks like. The light is incident upon this barrier. As it passes through these slits, it spreads out and starts to interfere with itself. This is proof positive that light is a wave. But we also saw the photoelectric effect, which is proof positive that light is a particle. As far as how to explain that, good luck. This is actually one of the great mysteries of quantum mechanics, is why this is the case. But in some ways, the role of science is not to answer that question. Why is the universe like it is? The role of science is to say, given the universe as it is, can I describe it mathematically? And turns out, yeah, we absolutely can. In the case of quantum mechanics, the mathematical precision of quantum mechanics is quite robust. So light is this thing that is not just a wave and not just a particle, but is somehow both and acts like one or the other depending upon your application. So we call this, in general, the particle wave duality. This idea that this thing which acts definitively like a wave at some point can act definitively like a particle at other points. All right, that's the summary of what we've got so far. If you think that it's weird, just hang on. It's going to get weirder as we go farther into quantum mechanics.